This section is quite a bit of fun, and it's called proportional parts. The idea is that, let's begin with the original triangle, this really nice big large one here. And then what we're going to do is we are going to send parallel lines through it. And these parallel lines are parallel to this side down here. So what happens when we do this, it cuts the triangle up into lots of little pieces. Cuts it up into this little piece, cuts it up into this little piece, cuts it up into this little piece, and so on. Now the cool thing is that it cuts it up proportionally on the opposite side as well. In other words, they're not equal in their relationship, but the piece cut here compared to that one will be the exact same ratio as this piece to that one, as this piece is to that one. So when you cut things up, and why would this be, by the way? Well, the answer is these are each similar triangles. This little tiny guy has the same angles as this guy, has the same angles as the big guy, because again, these are all parallel lines that are cutting this up. So the similarity then says, oh, well, okay, if the big guy is, or this little guy is ABG, it would be similar to, let's see, ACF. And it would be similar to the next one, ADE. Isn't that cool how, again, this little guy right here is similar to this guy right here, who is similar to this guy here. And because of that, all of the little pieces along the way, all of these little pieces get cut proportionally by those lines. And this creates all kinds of fun. So this becomes a fun little thing. Any set of lines like this that are cut transversals, parallel lines, you get all kinds of wonderful little pieces and parts that are in ratio. So let's go over here and look at the ratio they give us and see if we can solve for it. And I'll try and use some color to help us out. So it says BY on this side, so that's this piece, is compared to BD on this side. So we're comparing this little piece compared to this little piece. So if we're going to do that on the opposite side, we would do, as it says, TM. That makes sense. Now, who would match the BD? Of course, it would be TE. And so our answer would be T2E. All we're doing is following the same pattern of this little guy got compared to this guy. This little guy would get compared to this guy. We don't know any of the values, but we know that those would have to be proportional. They're not equal. The scaling is equal, but the values would be proportional. Next, let's do this ratio here. AY, all right, way up here. AY is compared to AM. Ooh, this is interesting. So if we were to follow a similar pattern, DY, so the one on this side, would definitely be compared to this guy over here. So again, follow the logic is they said, all right, from A to Y and from A to M in that order. So we would follow the same order. That would be DY is to EM. So EM would be our value, E to M there. Cool, let's do one more. In this case, they go TE, all right, that's this guy, and they compare it across to DY. Oh, okay, yeah, TE to D, BD. And then they say, now let's compare something to AD. So let's follow the pattern of the proportion. TE, this side, gets compared to its opposite side, BD, in that ratio. What that must mean is it would be from here to here. So AE must get compared to across at AD. So it would be, I think, what is that? AE would be our value there. The key is whatever this pattern is created between these ones or these ones, you follow the exact same pattern. Let's do some calculations now. Now in this question, I'm actually going to show you many ways that this could work to prove the point. So I might say to you, you guys tell me an answer. And someone might say, oh, I got it. 5 is to x as 6 is to 4.5. And I would say, you are awesome. And I'd say to the student body, somebody give me another one. Oh, and someone would say, oh, I know what to do. 5 is to 6 as x is to 4.5. And I'd say, haha, you're awesome. That is actually correct too. And I'd say, someone give me another one. And they'd say, well, let's see. Let's do 4.5 is to 6 as x is to 5. Now, the truth about all of these is they would all work. Now, I want to just mess your mind up just for a minute. I might say to the students, give me one more. And let's see if you can see what this person did. They might do 6 is to 10.5 as x, or 5, is to x plus 5. This also would give me the same answer. Now, I hope some of you are going, where did he get this 10.5? Maybe some of you know. Take a look. It would be 6 is to 10.5, which would be the full length here, as it would be to 5 as its full length here, which is 5 plus x. Now, no matter who you created here, when you cross-multiplied this, no matter who you did, and doesn't matter which one you did, you would get x equaling 3.75. And so part of what I'm trying to teach you here is, do you see it as going across? Well, if you do, that's perfectly fine. Do you see it as comparing between the ones on the same side? If you do, that's perfectly fine. All of those will work as long as you keep them proportional. So the key is to find the value that we're missing, which is the x. That probably means we're going to use the 4. Now, how do we get everything else going? We need a scale factor. Those guys have an unknown in them. Oh, I see. They're going to use this little 1 here and this little 1.2. So I think the way we would do this is maybe, in many ways to do it again, we might say 1 is to 4. So this number is to this number. As 1.2, this number is to its partner, which is x. That's one way that could have done. Again, you could have said 1 is to 1.2 and compared going across, which is fine, and then simplified that out to be equal to 4 is to x. All of those, when you cross multiply, give you the exact same answer of 4.8. All right, we're getting to the more difficult ones, so pay close attention. I've done this long enough to know exactly what students will say. Let me write it down and let's see if you can find the problem. 5 is to 9 as 6 is to x. Now, I can't tell you how many students write that and how many times I got to tell you that that's wrong. Let's take a look why. Here's the 5 from here, and we're comparing to the 9 here. Then over here, we're saying it's the 6 here. That looks good. And then we're comparing to the x here. Do you see the problem that the 9 number that you used is not the same as the x number that was used here? So you got a couple of ways to work this out. If you want to use the 5, good idea, and use the 9, good idea. Then on the other side, you got to use the 6, all right, same good idea. But we wouldn't use x, we would use 6 plus x as an answer. If we cross multiply that out, we'll get a correct value. Let me give you a whole nother idea. This number was 9 right here. So actually that would mean that this is a 4, because if this is 5, 4 and 5 make 9. So actually, if we had done that calculation, you and I could have also said 5 is to the 4 piece, not the 9, but the 4, as 6 is to the x. Whether you use this guy or whether you use this guy, when you cross multiply and solve, you get 4.8 as this guy's answer as well. Now, one last warning and problem ahead. Pay attention coming. All right. Warning, warning. All right, pay close attention. I've been doing this game long enough to know that this is probably in the top 5 errors of all geometry students. So pay attention to what I'm about to tell you. Pay close attention. Warning. The ratio that's formed between the proportional parts is not the ratio formed between the triangles. So I'll show you what I mean by that. We've already kind of talked about this previously. But here's the key idea. It says, when solving for full sides of a triangle, you must not use the proportional ratio. This is the most classic error. Let's show you what we mean by this. I've been at this game a long time, so I need you to pay close attention. I haven't done warning like this in a long time, so pay close attention. A student will receive this problem, and what they will naturally do is they'll say, 7 is to 14. All right, I got you. 7 is to 14. Now notice that 7 is a side of a triangle, but 14 is a piece of a triangle. And then what the student will do is go, oh, that will be the same as 5 is to x. Now I need you to understand that we just spent time talking about what is proportional. This is proportional to this, as this is proportional to this. That would be true. Or this is proportional across. But these are ratios of pieces of the sides. I need you to notice that the 5 is not a piece, it's a full side. And x is not a piece of a side, it's a full side. So if you tell me that 7 is to 14 as 5 is to x, you will get something that is absolutely wrong. So what we needed to do is this. Pay close attention. I would use my 7 is to 21. There's the important switch there. Where's 21 come from? 7 is to 21. Ah, I see the 21 as 5 is to x. And this gives you the correct answer. The key, my friends, is that those proportional parts that are so wonderful to use, and they really are wonderful to use, is that the problem is, though, that it can't be used when solving for a full-length side like this. Let's show you the last part. All right, let's see if we learned anything. What do you think? Do you think we did? All right, student 1. This is the wrong student, by the way. They go, oh, this is easy. I remember this. 8 is to 6. 6 is to x. Why is this wrong? You tell me, but I'll say it because you can't talk to me. That's because 8 is to 6 compares pieces of sides. And then when I compare 6 and x, those are full-length sides. So a correct student would say, pay attention, 8 is to 14 as 6 is to x. And when we cross multiply and solve that particular problem, we are going to get the nice value of 10.5 as the value. Now, again, why does it have to be done this way? Is because this is a full-length side, this is a full-length side. So I must use 8, that's a full-length side, and 14, that is a full-length side, when solving for these parts that are not proportional pieces. Beware, friends.